So let's start today's discussion on Eigenstate's thermalization hypothesis. So this is title Eigenstate thermalization hypothesis. So basically, this Eigenstate thermalization hypothesis is being a hypothesis. So it has no proof, but we can set up some verification with some mathematical constants. And in some instances, some experimental and some system we can consider, and then we just move on to the thermalization. So first of all, this thermalization is exactly mean the expectation or the average of any local observable or the measuring observable. So what does it state? It states that any local observable, the expectation of the local observable are uh, going to become a thermal equilibrium state or reach the thermal equilibrium state at a long time. So for the to so first of all we can start to understand about some equilibrium statement. So actually, why this equilibrium statement I want to emphasize in the beginning of the Eigenstate thermalization hypothesis, since the Eigenstate thermalization hypothesis may concern in the physicist mind that they want to know how much time a quantum system will take to become thermalized or something, so or may reach to the thermal equilibrium. So first of all, we know about the classical thermodynamics and the equilibrium statement. So in any ensemble of system where you can choose energy state, maybe eigenstates in, so let's choose an ensemble. So basically, what does the ensemble means? The ensemble means is the set of the copies of identical systems. So that's the thing. So where you can choose eigenstates for an ensemble, the identical some ensemble eigenstates is maybe stated as the kate in with some classical probability. So this is the your eigenstates. So what is going to happen when you take some average of the local observable? May set this A. So this local observable is going to some have uh, or state something P of n in equilibrium uh, times some expectation value of this local observable, and which is a sandwich with the eigenstates in. And it's definitely something gives us in something another notation the trace over the density matrix, that's the equivalent so of A, and where this density matrix it's basically defined with some m pn eq. So these pn's are the probabilities or the equal probabilities, so which leads you to the microcanonical ensemble. So I just state you so this ensemble. So if you may suggest that you have some classical probability p alpha, then your density of states will go something rho alpha p alpha alpha alpha. So this is the considered on an ensemble where you choose the orthogonal states, that's the alpha. So then your density matrices look like this. So this is the general density operator of the on diagonal, sorry, off diagonal in other bases. So this is something known as the general densities operator off diagonal in other bases. So off diagonal in other basis. So this is the statement of the density matrix, and then the eigenvalues of rho of the probabilities and the eigenvectors are states which are choose with those probabilities. So Gibbs description. So Gibbs describes something. So I just so Gibbs paradox or the Gibbs description, what you have known in your undergrad courses, that the Gibbs description is shows that equate that von Neumann entropy. So what he suggests that equate the von Neumann entropy, this entropy of these classical probabilities with thermodynamics entropy maximized to get P and Q. So suggested of these classical probabilities with some thermodynamics entropy which get maximized to get so equilibrium of n. So this is the probability of the equilibrium of the eigenstates n. So how do you get this P and Q? That you have to set up some von Neumann entropy with some classical probabilities with the thermodynamic limit. So in this entropy you can maximize this thing, and to find that this is something the probabilities of equilibrium probabilities, so the classical probabilities as P and Q. So how could you get this? It's look like so it's look like so your S would be something sum over n Pn of EQ ln Pn of EQ. So in other words, you may heard the name of that is a Shannon entropy, and so this is your entropy, and if you just maximize it with these probabilities, so delta Pn EQs is equal to 0, you can get so subject to the other constraints, so you can get this P and Qs from the thermodynamic sets of the classical probabilities. So now we dive into the microcanonical ensemble. So microcanonical ensemble is basically state microcanonical ensemble. So basically microcanonical ensemble is basically when the system has some fixed total energy. So system has some fixed number of total energy. So in when this system is have fixed number total energy, sorry, fixed total energy, so then your classical probabilities are the equiprobable. So all the accessible microstates have some equal probability. So that's the microcanonical ensemble basically described in its form. So that P n EQ is something 1 over some omega E if En is basically E and 0 for otherwise. So this omega E is basically the number of states. So if you have some large degrees of freedom, then your accessible microstates are being more higher and higher. So that's the thing. So this is this basically a microstates or the accessible microstates, or maybe you can say that this is the number of states with energy something E, with energy E. So this suggests that the equal probability. So your rho would be given as something 1 over the total number of microstates and sum over n. So when n is belongs to something En equal to the some fixed energy which is E. So in that and let's move on to some canonical ensemble where we can allow if the two systems are close enough and connected with each other, and if we uh, allow to communicate well, between these two systems with some energy flow, or if you allow to pass the energy from higher energy to lower energy, like something diffusion or so. So as the higher energy states will move towards some have some flow of towards the lower energy state, so the system would get some the average of the observable would get some equilibrium. uh, so uh, that leads to your thermal equilibrium. So if you go or dive into some canonical ensemble, so there the system has fixed average energy, not the total energy. So the main difference between the canonical and the microcanonical is that the system have some fixed average energy. So in canonical ensemble where the system has fixed average energy. So then you would expect something Boltzmann weight. So your Pn, so some classical probability at the equilibrium, that should given you that 1 by z of time of beta. This is the partition function, e to the power minus beta of En, and this rho. So your density matrix would be 1 over z of beta. So beta is 1 over kt, e to the power minus beta h. So h is your Hamiltonian, and this z beta is known as something Boltzmann weight. Boltzmann weight. So basically, this Boltzmann weight suffices that how much probability would be at the energy E or E1, E2, and E3 if you have some copies of the same energies. That if you have some n number of copies, then your canonical ensemble, if that then you would expect that your average energy will be fixed. So it is some upper bound En, that there is no beyond there is no energy, the value of energy beyond En, because that is the some average energy. So that should be fixed in the canonical ensemble. So and your z beta, this is a partition function or the Boltzmann weight, whatever you may named, that should be the trace over e to the power minus beta h, if h is your Hamiltonian. So now the question something arises to uh, think of the some averages, that is the ergodic average and ensemble average, time average, and so on. So there are lots of physical averages we may encounter in our studies of physics. So first question of manifestly, so how does the dynamics manifest the reversible in microstate T and to lead to the irreversibility? So you can ask some questions. So that questions leads you that your these hypotheses are more precise in some physical system, and it has some experimental verification. So, first question you may ask, to answer this question, that hypothesis realized or the hypothesis generates. So that hypothesis, the first question: how does dynamics manifestly manifestly reversible in time lead to irreversibility? Irreversibility. So this is the microstates T. And the second question you could ask: why do the detailed initial condition not matter for the thermodynamic quantities? Why do the detailed initial conditions not matter in thermodynamics? So as you see, if you solve any dynamical problem that leads to some time dependent, may Schrodinger equation or may the Newton's equation. So when the time is involved, then you require to know the initial condition, otherwise you can't solve this kind of differential equations. So or you cannot predict the trajectory or some dynamics of that particle. So so initial conditions are very much necessary thing to solve or to realize a system or solve some dynamics of from the Newton's law or maybe the time dependent Schrodinger equation and so on. So but in thermodynamics we does not care about what the initial conditions are, because we are dealing with basically some average quantity and some macroscopic elements. So these are not the some individual tiny points, which is the microscopic quantity. So when you are dealing with some macroscopic quantities, and it doesn't matter what are the initial conditions and so on. So that's the thing. And next question: so will all closed system, closed, or maybe closed means the unitary, so the system follows some unitarity, so maybe I just unitary quantum systems lead to uh, lead to a statmic equilibrium or the statmic equilibrium description at long times. So at long times. So these are the another questions. And where are the multiple copies of ensemble that we use in the Gibbs description? So if you have a system that loaded with some gas, maybe your macro states are P and V, and if you attach another system which may have some magnetization and so on, so if you have some random directions in the box, so if you just allow to exchange energies between the system A and another system B, then what you would expect that your pressure versus time, so that your uh, plot would may be oscillate somewhere and uh, becomes some making some thermal equilibrium at a long time. So it's a classical description of the equilibrium, that if you have some large macroscopic quantity pressure and volume in some units, and if you have another system which have some random magnetization, then what do you expect, that the expectation or the average of these macroscopic quantities, that leads to a thermal equilibrium at a long time. But when you state about the quantum mechanical thing, then you does not find any kind of this macroscopic variables. So what you can do, so you have some local observable, so that observable would goes to thermal equilibrium at a long time. So that's the main idea of the eigenstate thermalization hypothesis. So the system would get thermalized at a long time. And how do you check this? That the expectation of your local observable or the measuremental thing, that would get some thermal equilibrium at a long time. So that's the basic concept of this scenario. So first, to know this idea, so first of all we just set some concept of the time average and the ensemble average. So it's a basic definition that you have learned in your undergrad days, but I just recall this part to understand this hypothesis. And this is introduced by Mark Srednicki, and it's 1997 and so, and then later he wrote another paper is at 2007. So first he introduced this eigenstate thermalization hypothesis with the help of some random matrix theory, and then he suggests that the mixing of the elements are, or the some variance or the fluctuation of these matrix elements are goes to or leads to thermal equilibrium. So that's the thing. So first we had to know that what are the time average and some ensemble average. So basically the so if you just proceed to some thought experiment, that think of the large number of people in a people crossing a busy junction every day, and interested the average number of people meets their friend at the junction. So there are the two conditions. So in case of the time average, what you would expect, so you can make some experiment that the large number of days you have some large number of days and count the number of friends meets on a single person at that junction. So basically what you do, so if you just go to a railway station, and lots of people are coming and going out from this from the entry and exit point, and at that junction you just uh, reach every day at the same time, and for a week or maybe for a year, so count the large number of days, and you just calculate, you just count how many friends you have made at that junction point at the same time, uh, and for a large number of days you just go and so on. So you just make this experiment for a week maybe. So these are 7 number of days, and you just count that the first day you may meet some two friends, and then three or maybe seven, and so on. So at the end of the day or the end of the week, you just average out with the number of days you visited that place or visited at that junction, and how many friends you have met. So that will give you some time average. And the ensemble average is the basic thing that count the number of friends a large number of at a large number of people meets at a junction time in a day. So it's a one shot problem. You just go, or maybe the large number of friends visited there, and you just go there and count the how many numbers of how many friends in a total of that whole volume class or the whole volume people, and then you just think of uh, that the the ratio of people and the ratio of friends and all that. So that probability or that average would give you the same thing or equivalent to same thing in a one single day. So it was one shot problem. So your basically it's reduces a risk that the large number of time gives you some error. So that is the case of the ensemble average. And now you can ask that the when these two things are same. So basically that leads to a ergodicity, and for many typical initial conditions and system explores the all possible states at the same energy as you wait till infinity. So that's the case. So it is a one day problem, and the time average is the large number of day problem. So that's the basic difference between the time average and some ensemble average. So now this the question of some mixing from many typical initial condition as you wait till infinity, and the system has some equal probability to explore each accessible states. So that's the phenomena of the microcanonical ensemble. So if you wait till a large time or for a long time, then you could expect the time average is also equivalent to your ensemble average. So that's the thing. So when the time average and the ensemble average are being same, but typically both the scenario of calculating the averages are different. So that is the case that we are looking to. So I hope that you already understood that the averages. So now I just goes to a system and discuss that eigenstate thermalization hypothesis. So basically, this eigenstate thermalization hypothesis. So in this lecture, we just point out some common formulation of ETH that suffers from for a mixing of the random deterministic variable, and we suggest some modified formulation that gives by some physicist, and that suggestion is typically verifies that these hypotheses are basically true. So as this eigenstate thermalization is a hypothesis, so it has no some definite proofs and all that, so we can verify with our analogy, and then we just go to deep down, um, and to this end we can ensure these hypotheses are being true for physical systems, and it is experimentally also being verified, I hope. And it is easy to verify, and you can propose these eigenstate thermalization experimentally and so on. Okay, so so it is the very hot topic actually. So if you consider uh, so just consider bounded isolated system. So isolated system means there is no influence with some universe, and bounded means it has some fixed or fixed values or fixed values of average energy. So that's it. So it's maybe possibly the case where classically we just analyze the canonical ensemble. And the system has some large degrees of freedom. So the number of particle is much greater than 1. So since this system is bounded, then we can expect that your energy eigenvalues are discrete. So basically H of alpha is basically giving you the E alpha of alpha. So that's the thing. And these E alphas are the discrete eigenvalues. So why it's a discrete eigenvalues? Because the system is bounded. And since and the system is isolated, then you can have some time dependent wave function psi t, that is basically your discrete number of states, that alphas, and you have some amplitude, that C alpha, and some would get has some unitary phase, that E alpha of t of psi, or maybe I just some orthogonal basis is alpha. So this is for bounded, and this can be written because the system is isolated, right? Okay, so it's as usual that your psi t is basically sum over alpha C alpha square, and it's orthogonal and it's a normalized, it leads to you 1. So that's the thing. And of course, to get some thermal case, so you have to have the system of the thermodynamic limit, that's a large number degrees of freedom, large number of degrees of freedom, that suggested by n is much greater than 1. That's it. I hope it's a basic quantum mechanics. So now we just go the how the classical system goes to a thermal equilibrium. Now we would expect or realize. We want to realize for a large degrees of freedom on the many body systems, uh, how this system would reach the thermal equilibrium at a long time in a quantum mechanical way. So it's basically quantum thermodynamical equilibrium. So in a quantum, so not is basically the quantum thermodynamics. It's not actually quantum thermodynamics. So we deals with some classical probabilities and all, but we think or we want to realize how the system goes to thermal equilibrium in a quantum mechanical way. So it's the basic quantum mechanics for a large number or the many degrees of freedom. So that's it. So I just uh, so I just erase the board to get some spaces. So let's an observable. We are interested to be a smooth function of the classical coordinates, and the moment which has no explicit dependence on h, and your Hermitian operator may be a, which corresponds to this observable, that leads to some a alpha beta, and which basically defined, or the definition, this is the matrix element, that a of beta. So that's the case. So now what do we? So according to Srednicki, that the is the if these matrix elements are there, then your alpha beta, that some quantum chaos theory, the Srednicki suggest this a alpha beta of the form of some a e alpha, where delta alpha beta, this is a diagonal term, and plus some of diagonal terms are h cut over n minus 1 over 2 r alpha beta. So it's an exponentially small number thing. So here AE alpha would be a smooth function and of order 1, smooth of order 1, and so as the we just consider the leading order of R alpha beta, so it's also being order 1. Okay. So this is basically smooth distribution. And later, the Srednicki also suggested for the formula of the matrix element of the energy eigenbasis in his later paper from the random matrix theory, that your A alpha beta would be some AE alpha. The first term of the diagonal components are being same because it does not bother us that how it goes, because it's already in some deterministic thing. And now the question is in the mixing with the off diagonal element, that he suggests that e to the power minus s, this is a exponentially small thing. So Se is the entropy, so thermodynamic entropy of having some energy E, and another some smooth function would be there, and R alpha beta, the off diagonal elements. So this is the exponentially small thing. So our expansion is the leading order is something exponentially small thing. So and it's some smooth function. Okay. So so how do I understand that this f e omega is basically greater than 0, even function of omega. So even in omega and smooth function of both arguments. So and smooth, so it's a smooth function. And R alpha beta is a random variable, varies erratically with alpha and beta. So it's basically the off diagonal thing, and it's something order of n. So basically, so for many degrees of freedom, when in large enough, then entropy is supposed to be extensive. So as entropy is supposed to be extensive, then S of En may be some n number, so order n number, that function of E over n, and something order of ln n. So this formula refers to be the ETH ansatz or the Srednicki's ansatz. So this is something ETH ansatz, right? Okay. Okay, so next we consider that a Hamiltonian, that H is something H0 is a original Hamiltonian or unperturbed Hamiltonian, and another term is some weak perturbation, that is the V, and that refers to a two-body interaction. And due to this Hamiltonian of the system, of the many body Hamiltonian, that V refers to some resemblance of a random matrix, because V is basically the perturbation, the weak perturbation, and refers to some two body interaction. So it offers you that the off diagonal elements. So this is the random off diagonal elements. So you can think that total H, the total Hamiltonian, this H is basically a random matrix. So however, this is the Hamiltonian is not true, is there is a deterministic value of LHS of the ansatz, and but the RHS includes the random matrix variable. So for the given non-random Hamiltonian, the ETH suggests, so given non-random Hamiltonian, ETH suggests that your formula will be A alpha beta, that your matrix element, that A of E delta alpha beta, that's the on diagonal thing, and e to the power minus s by 2 of the energy E of this entropy is being measured, and something G alpha beta of E and omega. So there is no alpha beta because when you think of that G alpha E omega is bounded, is a complex valued and non-random, because this is a function is smooth of both arguments for a large degrees of freedom. So so it is non-random for the non-random head. So there is no something called R alpha beta. So that mixing, and these are the smooth function. Okay, so G alpha beta. So that formula ETH suggests. And what does the ETH actually do? That if you plot something T and your observable A, then your observable go reach the thermal equilibrium at long time. So for the thermal equilibrium, so this value is basically ETH or A thermal of the thermal average of that your observable. So this value leads to your thermal observable. So basically, why? Basically, I just replot this. So this value is A thermal. So average of A thermal, and this is something expectation of some local observable, and this is axis is time. So this actually suggests that any local observable of for a closed and isolated bounded system, it goes to a thermal equilibrium at a long time if the system have large degrees of freedom, so n degrees of freedom. So your so thermal formula would be trace a to the power minus Hamiltonian over T times A, and that's the Boltzmann weight minus H over T. So this is the your expectation value of the thermal average. So T is basically del of E over del of S. It is the argument that A approximately equals to, so your this AE, the diagonal thing, which suggests from the expectation of the local average in quantum mechanical way, that is equal to the thermal average, that whatever it is written here from the trace e to the power minus beta h and all. So the beta is the Boltzmann constant, so it's basically inverse temperature. So that is basically equal with your this thermal expectation. So if you consider spin systems, or maybe systems with large number of particles in a closed V volume box, then you would expect, if you just allow some exchange of energies, then classically you would expect that it reach towards the thermal equilibrium as it is being realized by this quantum mechanical scenario. Okay, so now we just goes to two basic verification of some theorems, or suggest some theorem for the deterministic formulation of ETH. So then we can ensure that it is okay. So suppose that this deterministic ETH formula, that the formulation that the ETH holds for a large degree of number. So you can whatever. I just look up some asked a question for to explain this kind of thing. So let me give you a second. So so by the definition, so you may set some definition that the system is in thermal equilibrium at time t. So definition is gives you a system in thermal equilibrium at time t if your operator expectation minus a thermal, this value should be some epsilon. Epsilon is some experimental tolerance. So that's the for the set of A's. So you can ask some question that can we get some thermal equilibrium at most times for T for all your eigenstates psi. So with some fixed average energy, as I mentioned, and some finite fluctuation of your energy, fluctuation of energy. So answer is yes. So that you have to think that this your AE operator expectations, some thermal expectations is basically exponential small number. So order of inverse of n. So if we reproduce here the detailed the proof of this ETH answers, then you just start with something partition function that z a of t, it's your numerator thing. So your numerator is basically trace of e to the power minus h over t and a. So it gives you some alpha e to the power minus e alpha t. So it's I just take the Boltzmann constant is equal to 1, the standardized. So this is the diagonal element a alpha alpha. So your the system is goes like this, e to the power minus, so minus u over t delta u minus e alpha du a alpha alpha, and it leads you that exponential of minus u over t sum over alpha delta u e alpha a alpha alpha du. So we have this that sum over alpha delta e minus e alpha is basically would give you e to the power s of e over e. So from your von Neumann and Shannon entropy case at that energy values or the at that in a discrete energy level. So that should be this. So your ZT, so I just erase all the thing. So your ZT would something 1 by u exponential of SU minus U over T AU du plus 1 by U exponential of SU minus U over T of order of exponential SU over 2 times du. So, and your denominator would be some z, this is a partition function that basically gives you some trace over e to the power minus h over t, that leads you 1 over u exponential of SU minus u over t du. So there is no AU. So it's something numerator of the thermal average and it's the denominator of the thermal average. That's it. So by the Laplace method, so you can trust that your AT, that is your AU, just take a ratio of this numerator and denominator plus order of exponential minus 2 plus order of n minus, because a large number of large degrees of freedom. So it is become some operator expectation plus order of so on. So this statement, this is the original statement where we start that the definition of ETH answers that your operator expectation and the thermal expectation would become or nearly equal at a long time. So that's the thing. I hope it is easy to see. And another condition, you just have to, you may have seen that suppose you have some psi t for the isolated system, that you may think that is the alpha C alpha e to the power minus I E alpha t over h cross of alpha. Then this time average, so infinite time average, that two things that quantum mechanically you can see the expectation value of an observable, that AT is basically psi t A psi t, which gives you basically alpha beta C alpha, so star C beta and e to the power minus I E alpha minus E beta of t of A alpha beta. This is the off diagonal thing, the matrix element. So, and another just time average, so may I just written up A bar, which is limit tau tends to infinity. So time average, you just take a long time average. So that's 1 over t, or maybe I just write tau without making confusion between temperature and time. So that your 0 to t or tau at dt, and where your energy is basically C alpha square E alpha, and the fluctuation is basically alpha C alpha square E alpha minus square. So this is a quantum uncertainty of the energy. So this is the energy uncertainty. Certainty, and it is your average. So it is your expectation of energy, right? And you may see that this part, if you made it up square, the C alpha square, and so like this way you can think that your AT minus A bar, infinite time average, this square, and that leads you, if alpha not equal to beta, that C alpha square C beta square with some A alpha beta square should be less than of your expectation to experimental tolerance, that epsilon square. So this also being a suggested thing, that it is your squared. So basically it's a standard deviation, it's like a standard deviation of the energy fluctuation and the uncertainties, the quantum uncertainties of the energy. So this is the notion. So we just make it right that if these are the definitions, then we just want to show the two conditions that, so infinite time average, this A bar, we want to show these two thermal plus uncertainties is basically order exponentially small, order n minus 1, and the fluctuation, that AT minus A bar square is basically order of the exponentially small of the thermodynamic entropy. So, so let's start this proof. So we want to have these conditions are to be proved, that your AT psi of TA psi of T, which basically essentially gives you C beta alpha beta. So essentially this is C alpha squared, the diagonal element A alpha alpha plus alpha not equal to beta C alpha star C beta e to the power I alpha minus E beta T of A alpha beta. And our time, infinite time average for the non-degenerate energy eigenvalues, that limit t tends to infinity 1 by tau 0 to tau, and hopefully this all the things C alpha square A alpha alpha plus C alpha star C beta e to the power I E alpha minus E beta T A alpha beta, and that leads you something C alpha square A alpha alpha. So generally in the integrable system, most of the off-diagonal things are B0. Most of the matrix elements are 0. So now use the ETH ansatz So if you just use the ETH ansatz, then probably you'd have this A bar is something alpha C alpha square A E alpha plus order of e to the power minus S E alpha over 2 is basically equals that. If you just do some simple algebra, then you can reach that A, just separate it out, E alpha plus order of minus AC over 2. So that's it. And for case of A bar, so if we just do Taylor series expansion of AE alpha around the A bar, so average, so Taylor series would suggest that is AE plus A prime of E, add up E alpha minus E plus A double prime of E, E alpha minus E square, and so on, and the large order. We just take it a small perturbation, so we just substitute it here, and would find to the end of this calculation would find that this AE plus order of these fluctuations plus order of AC over 2. So just if you just substitute this Taylor series expansion at this point AE alpha, so that's the case, and there is a simple algebra, you can find it very easily. Okay, so now for the last statement, why the system are supposed to have some integrability or the unitarity for a large number. So basically for a large number of systems, so ETH may hold, some system may don't hold. So basically when the system refuses to Eigenstate thermalize, then it leads to something many body localization. So that is another scenario to understand some Anderson localization and the many body localization. So for this now, so we just restrict ourselves in this, that A bar square, that limit tau tends to infinity 1 over tau 0 to tau AT A bar square dt, it's tau infinity 1 over tau AT square dt minus A bar square. So if I think of this AT square, it leads you something alpha gamma C alpha square C gamma square. So it's the diagonal thing, A alpha alpha A gamma gamma. So just the term indices and make it squared. So alpha and gammas. So alpha beta not equal to alpha, then C alpha square C beta square plus sorry A alpha beta, A beta alpha, and some other terms will be there, other mixing and coupling. So basically this 80 square we obtain up to the this diagonal part, and if we extend this thing, that another term we can write that is minus alpha gamma C alpha square C gamma square alpha alpha gamma gamma, to basically I just mean to write this thing 80 minus A bar square and then average the fluctuation that's is equal. So this whole term is equal to some C alpha square C beta square A alpha beta square, which is less than equal to the maximum alpha not equal to beta A alpha beta square alpha beta C alpha square and C beta square. So basically it's equals A alpha beta square. So basically this distribution, if you see that the probability versus the probability and the diagonal element A alpha alpha with some E alpha, so you can see in that some energy window, within some energy window, so you can find something C alpha square which leads to be your amplitude and goes to a Gaussian. So and when just we reach here, so we can end up our story that this means that maximum alpha not equals beta A alpha beta square of something. So this is basically equals maximum alpha not equals beta order of exponential minus s, that E alpha plus E beta over 2, that leads you basically the order of e to the power minus AC, and this is something order of n. So that's the two statements stated that the expectation average and the thermal average are going to be same. So maybe very precise way, so you can think of that your average energy is something order n and the uncertainty of energy something n to the minus nu E bar. So this is maybe the scale of your average energies and the uncertainties of energies. So that two conditions and that two theorems are leads us that the eigenstates thermalization hypothesis, and it is very evident, but it is not holds for every many body system. Some systems are refuses to eigenstate thermalize or refuses to thermalization. So that leads you to the Anderson Anderson localization, which is as known as the many body localization. So we may discuss it later. So the hypothesis that is made by Srednicki from his quantum chaos theory and some with the help of the random matrix theory, they suggest or propose this hypothesis that the expectation value of the local observable and that leads to the thermal average at a long time. So that's the statement, and the main keynote that is whatever we can suggest that how much time that any local operator requires to get thermalized in quantum mechanical way. So we have all the information in the classical mechanics and in the classical probabilities with the help of classical probabilities and so on. But now we just understand and realize the thermalization and the equilibrium, the thermal equilibrium in quantum mechanical way. So it's a Eigenstate thermalization hypothesis. Okay, so for today it's enough. We just end our lecture here, and it is the very good time to stop to digest this ETH. Okay, thank you.